Welcome to Introduction to Composites. In this week, which is the 10th week of the course, today is the 4th day in particular, and what we plan to do today is continue the discussion which we had yesterday, close that discussion and then move on to a new topic which is about failure of composite materials, specifically when individual layers of composites, especially orthotropic sheets, when they are loaded in a plane stress state and when they fail, then how can we predict their failures. But before that, we want to complete the point of discussion which we had earlier. So, what we have shown is that we can now calculate sigma x, when you measure stress in with respect to x and y plane. So, that is equal to a matrix q bar times a strain vector measured with respect to x axis, and we know how to calculate all the elements of q bar matrix. Similarly, we can also calculate strain in terms of a S bar matrix and the stress vector sigma x y. Okay. And how do we do that? We actually just do exactly do all the steps which we have discussed earlier, so we convert all these in terms of L and T, and then we figure out, and using that we can calculate the elements of this S bar matrix also. The process is exactly the same. So, my suggestion would be that you please go and actually do all these steps, because it will be useful for you to understand. What I will do is, I will now give you the relations of all the elements of S bar matrix in terms of S matrix. So, S11 bar, and I am just going to give this directly. So, please go back and do this so that you are able to show for yourself that these relations are indeed correct and you are convinced of the results. So, this is equal to S11 times cosine 4 plus S22 times sine 4 plus 2 S12 plus S66 times sine square theta cosine square theta. Okay. S22 bar equals S11 times sine 4 theta plus S22 times cos 4 theta plus the same term times sine square times cosine square. Then we have S12 bar, this is equal to S11 plus S22 minus S66 times cosine square theta sine square theta, okay, plus S12 cosine 4 plus sine 4 theta, and then S66 bar equals 2 S11 plus 2 S22 minus 4 S12 minus S66. So, this is like this. So, it is twice of 2 S11 plus 2 S22 minus 4 S12 minus S66 times cosine square theta sine square theta plus S66 cosine 4 theta plus sine 4 theta, and then S16 bar equals 2 S11 minus 2 S12 minus S66 cos cube times sine minus 2 S22 minus 2 S12 minus S66 times cos times sine cube, and S26 bar equals this entire thing, but this is sine cube times cosine minus this entire thing times cosine cube times sine. So, once again we see that the first 4 elements are even functions for theta, and these 2 guys are odd functions of theta. Okay. So, S11, S22, S66 and S12, all these bars, if I change from theta to negative theta, the value does not change, but S16 bar and S26 bar, their values swaps from positive to negative if I make theta to negative theta. So, this is very important to understand and be clear about. Next, what we will do is we will do an example. So, what do we want to do here? So, we have a unidirectional lamina and I am applying some. So, it is the fibers are in this direction. Okay. So, this is my L direction and I am applying sigma x So, actually I am compressing it, I am not pulling it in tension. So, I am applying a sigma x which is compressive and that equals sigma x is 3.5 MPa, and then I am also pulling it in the transverse direction. So, that is the tensile load and that value is 7 MPa, and then finally there is also a shear stress and the shear value is 1.4 MPa, and this angle theta is 60 degrees. So, remember we always measure with respect to x axis, going counterclockwise is positive theta. So, theta is 60 degrees. Okay. So, just to be clear, sigma x is equal to minus 3.5 MPa, sigma y is tensile. So, it is 7 MPa, and tau x y, because it is in the negative direction, positive direction we have defined earlier also. So, that its value is 1.4 MPa. And now what we will do is we will also give you the material properties. EL is equal to ET and that equals to GLT is 3.5. So, this is all GPa. So, tau xy is negative here, and the Poisson's ratio nu LT is same as nu TL. So, looks like this is a balanced lamina and this is equal to 0.2. So, these are the data, and the question is calculate we have to find strains in the x direction. So, epsilon x, epsilon y and gamma xy, these are the strains we have to calculate. So, there are several ways we can do this. What we will do here is we will first compute sigma L, sigma T and tau LT. I mean we can directly do the computation because we know sigma x, sigma y and tau xy. One way to do the calculation is we directly compute first the Q's, okay, using these relations. So, first we calculate Q11, Q22, Q66, from those we calculate Q11 bar, Q22 bar and Q6, all these bars, and once we have all this, then we use this relation and take the inverse of this relation and we can calculate sigma x, sigma y and tau xy, but we will use a slightly different method today. So, what we will do is first we will calculate stresses with respect to L and T coordinate system. Okay. So, sigma L, sigma T, tau LT is equal to so this is the relation we had talked about earlier. This is equal to sigma x, sigma y, tau x y, and this matrix is what? The transformation matrix T1. Okay. And what are the coefficients for this I mean the members of this transformation matrix? Cosine square theta, sin square theta, 2 sin theta, cosine theta, minus 2 sin theta, cosine theta, cosine square theta minus sin square theta. This is cosine square theta, this is sin square theta, and these guys are minus sin theta cosine theta, and this is sin theta cosine theta. So, first step is we are computing sigma L, sigma t, tau L t. So, so what is theta? Theta is equal to 60 degrees. So, cosine theta is how much? Cosine theta is half, sin theta is root 3 by 2. Okay. So, from this we find out the members of this matrix. So, what are those values? So, this is 0.25. So, I have 0.25, this is 0.75, and this is 0.866, 0.25 minus 0.866, and this is, so cosine square theta minus sin square theta is cosine of 2 theta. So, it is will be cosine of 120 degrees, right. So, this is 0.5, okay, and this is 0.433 minus 0.433, and this is 0.75 times sigma x. Sigma x is how much? Negative 3.5. Sigma y is 7, and this is minus 1.4. Okay. So, if you do all this, then what you get is 37 minus 12.05 and 57.4. This is 5.24. So, these numbers are incorrect. So, this is 3.16, this is 0.39, and this is 5.24. Okay. So, now that we have, so these are what? These are sigma L, sigma t, and tau L t or tau T L. Next, what we do is we compute. Now that we know this epsilon L, epsilon t, and tau L t. So, what do? We know that epsilon epsilon L equals S11 sigma L plus S12 sigma t. S16 is 0, right, and S11 and S12 we have already shown how to calculate from engineering constants. So, from these engineering constants we can calculate S11 and S12. So, this works out to be something. Similarly, epsilon t is equal to S12 times sigma t, sigma L plus S22 sigma L, and gamma L t is equal to S66 tau L t. So, we can calculate these things from here, and once we have computed epsilon L, epsilon t, and gamma L t, then from these we calculate epsilon x y using in the x y coordinate system. What is that? it is the transformation matrix to its inverse times strains measured with respect to LT coordinate system. Okay. Now, I will give you a trick to how to very quickly compute the inverse of these transformation matrices which are dependent on theta. So, suppose you want to calculate the inverse transform of inverse of this first transformation matrix T1. Effectively what that means is that you replace theta by minus theta and that will give you the inverse of it. So, the inverse of T2 when theta is equal to theta is nothing but you calculate theta by replacing it by minus theta. So, you put minus 60 degrees and you will be able to calculate the inverse of that, and that will very quickly give you the solution. So, if you do all that mathematics, and what are the elements in that T2 matrix we had shown earlier. So, here if you replace theta by minus theta, what are the terms which are going to change? This will go from positive to negative, this will go from negative to positive, this will go from positive to negative, this will go from negative to positive. All other things are going to remain the same. Okay. So, you do those replacements, and so that will give you inverse of T2, and then you multiply that by epsilon LT, which we know how to calculate, and then you get epsilon x, epsilon y, epsilon and gamma xy. So, epsilon x, it works out to be minus 481 into 10 to the power of minus 6, epsilon y equals minus, no, it is actually plus 704 times 10 to the power of minus 6, and gamma xy is equal to minus 442 times 10 to the power of minus 6. Okay. So, this concludes our discussion for today, and this essentially tells us how we can compute strains and stresses in a system even if it is not even if the direction of stresses are not necessarily aligned with the material axis of the system. So, first thing is in terms of engineering constants we calculate the Q matrix and the S matrix, and from that Q matrix and S matrix we can calculate Q bar and S bar matrices, and once we have those matrices in place, then we can relate strains and stresses in the way we want them to connect. So, this is the conclusion of our today's lecture. We will start a new topic tomorrow, and that is about failure of unidirectional lamina and different theories associated with failure of unidirectional lamina. So, with that I conclude our discussion, and I look forward to seeing all of you tomorrow. Thank you.